Yeah, thank you for coming along, everyone. Oh, I'll take that. Thanks. Thanks for coming along. So today we're going to be running a MATLAB primer. So my name's Jesse. I'm the president. We've also got Mohammed here. He's one of our execs. So basically, I'm just going to be running through some basics of MATLAB and maybe some few more advanced features that will be useful. So just before we start, I'm just wondering, who here is like Math 1051, 1052? Like pretty much everyone. Sick. Okay. Who's something else? Yeah.
Third year physics.
Third year physics. Yep. Anyone else? Okay. Well, at least we know our audience. Okay. So that's cool. So most of the stuff we'll go over will be stuff that you guys will do in your first year, not just 1051, but 1052. But then we'll also look at some stuff that's more useful for the physics labs, particularly stuff with plotting, symbolic algebra and stuff like that, which can greatly reduce the amount of work you have to do in lab reports. Okay, so to get started, what is MATLAB? So MATLAB stands for Matrix Laboratory. Basically, it's a piece of software that lets us do very efficient matrix calculations. You know, you don't want to have to multiply a 10 by 10 matrix by hand, right? But this software is designed to be able to do all of these sort of matrix operations really, really quickly. So linear algebra is obviously like the study of matrices and vectors and stuff like that, but it has a lot of different applications in different areas of mathematics. You'll see as you go forward into subjects like 1052 that you can also use algebra to solve systems of differential equations. And actually algebra rears its head a lot in physics as well. I'm sure you've seen in like third year quantum, it's pretty much just all linear algebra. So that makes MATLAB a really, really powerful mathematical tool. So why do we use MATLAB specifically? So if you're a scientist, well, if you're a mathematician, you can use it to crunch numbers basically and do lots of different computations. It's also a really powerful simulation tool. So a lot of people use it, you know, for their honors projects to write simulations, usually described by differential equations, and there's lots of different methods involved in that. I'm not going to touch too much on that today. That's not my area of expertise. I'm going to keep it a bit more basic than that. If you're a scientist, MATLAB is a really, really good tool for making graphics for reports and stuff like that. So you can make really pretty graphs. You can do 3D surface plots. One of my assignments, I simulated an oyster shell and made a graphic that showed the knacker of an oyster shell, basically. So you can do like really interesting, unique stuff. Yeah, and it's a very powerful tool for data processing, as I said before. So if you do measurements in a lab, and for example, if you're doing maybe a third year physics lab where you're measuring electric fluctuations of voltage in a wire, you might take 100,000 measurements. You don't have to sift through that by hand. You can do very efficient manipulations of that data and reduce it down to something usable. Okay, so let's get started. So I'm going to start very, very basic. So in MATLAB, you're going to be working with predominantly vectors and matrices. So we can create variables by assigning a handle to a variable. So for example, A, you can have an equal sign and you can assign some value. So something really simple would be to write A equals 1. You're assigning the value A, the value 1 to the variable or the function, or the handle A. And we can run this code. So at the moment, I'm typing in the script editor up the top. When I run the code, I just hit Control Enter. There's also a run button. You can see that down in the command window, we get some output, A equals 1. And we can also notice over on the right-hand side here, we have in our workspace, something saying A with a value 1. So basically, we write code in the script editor up here, we execute it, it runs down in the command window, and any of our outputs or any of the intermediate variables get saved in our workspace. So we can use those variables later when we write other code. So for example, I can even write code in the command window. I could do A plus 1, and you can see it gives me the answer is 2. So it went and pulled out that A that we had already, did some math, and gave us our answer. All right, so that's really basic. So what we actually want to do is start manipulating some vectors. So we can create a vector using square brackets like this, and we can just put in elements like that. So for anyone who knows anything about vectors, you know that we have row vectors and we also have column vectors. So this would be a row vector. If we run this code, you can see it just makes a row, 1, 2, 3, like that. We can create a column vector by doing the similar sort of thing, except now we use a semicolon instead of a comma to get it to go to a new line. So if we run this code, we can see now it's got 4, 5, 6 on separate lines. We can now do operations on these vectors. So I could type VU, but actually I can't. If I type VU, then the MATLAB just thinks I'm trying to talk about a variable called VU. Whenever we're multiplying, we should add a times in like that. And now if we multiply these, we get the answer is 32. Same sort of deal. I can't do 2u like this. If I try that, I'll get an error. Uh-oh, missing multiplication operator. So you want to always put your times in there in MATLAB. That's just a syntax thing. Okay. All right. So we can combine all that stuff that we just did to create matrices. So for example, we can create a 2 by 2 matrix like this. So we should see that we can have a 1 and then a 2. This will bring us down to the next line. Then we'll have a 3 and a 4. Okay, now we have a square matrix, 1, 2, 3, 4. And we can multiply matrices and vectors exactly how you'd expect. Oh, sorry, I made a 3 by 3 vector. If I make a vector x equals 1, 2, I can do ax, a times x, right? And run. No, what have I done wrong? Ax, a.
2 by 2, 1 by 2. It's not going to multiply. Matrix multiplication 2 by 2, 1 by 2.
Whoops.
Yeah.
That's all right. I will. Yeah, sorry. Good start. Okay, there we go. So as you can see, well, that's a good demonstration that when you have the wrong dimensions for your operations, it will not work. So you have to pay very, very close attention. And we'll get back to that in a moment. So that's not really an efficient way to create vectors. If I have a vector that I want to have the numbers 1 to 100, I really don't want to have to sit there and go 1, 2, 3, all the way up to 100. So what we can do is just write 1 to 100 by using the colon like that. Okay, and you can see when we run this code, it's created a vector v, which is we can see over here, a 1 by 100 double. So a double just refers to the type of number it is, right? It's different types of numbers. Okay, we can do more complicated things than that. We can create, for example, only the odd numbers from 1 to 10. So we start at 1, we move up in a step size of 2, up to 10. So this should have 1, 3, 5, 7, 9. And we can see if we run it, it indeed has 1, 3, 5, 7, 9. Okay, okay. We can also do something like this, where we start at 100, we step back in increments of 5 down to 0. So we can use negative increments as well. And I guess hypothetically, you can do like arbitrary decimals like this if you so desire that step size. All right, just note that it will stop before reaching this end bound. So if you don't have exact numbers, it didn't quite get to 0 because it won't ever overshoot this end bound. Okay, cool, so that's good. But what if we want to create a vector that has exactly 100 elements with maybe the numbers 1 through to 30? We don't want to have to manually calculate that step size ourselves. It's inefficient. So what we can actually do is use the linspace, which creates a linearly spaced vector. We can say, let's start at 1, go to 30, and make 100 elements. So now we get a 100 element vector. And as you can see, this step size was not a nice number. It would have been a pain to calculate that on our own. So it's much more efficient to just use linspace. And this is like useful when you want a certain like granularity in a plot, right? You want enough data points so you have a smooth curve. So you can use linspace to say, oh, I want to plot 1,000 different points or something like that. Okay, Another really important operation on matrices is the transpose operator. So there's two different transpose operators, if you know anything about transposing matrices. We have our normal transpose operator that we'd normally use, which is A dot apostrophe, and that just transposes a matrix. So for example, we can see A, and then A transpose is like this. We also have a second type of transpose operator. So if I create a matrix 1, I, 2, like this. So we create a matrix B, looks like this. So yeah, I forgot to mention, MATLAB can handle complex numbers as well, which is incredibly convenient because often, you want to solve problems with complex numbers. So now we have a matrix that looks something like this. We also have a different type of transpose operator, which is just the apostrophe. Just the apostrophe. And now we can see when we do the transpose, it actually takes the conjugate transpose or the Hermitian conjugate. So it flips like a normal transpose and also takes the complex conjugate. So you can see that these guys that got flipped across the diagonal now have a minus sign in front of their complex part.
Could you explain the syntax for that complex matrix? Why is there only one comma?
Oh, so you can leave the commas out.
Is that for any kind of matrix?
Yes. Yeah.
Oh, okay.
Yeah. You don't have to have the matrices. You don't have to have the commas. You can use white space. I usually put the commas in just because if you have a really big matrix, it's hard to, you lose track. Yeah. Transposing. So transposing is just flipping along the diagonal. So for example, this matrix here, anything along the diagonal stays on the diagonal because if it's flipping across the diagonal, it's not changing. But you can see that this 3 here got switched with this 2.
You
So
can also explain it as the columns become rows and the rows become columns.
yeah, so the columns become rows, rows become columns.
Yeah.
So if you look at the entry ij in your matrix, then it gets mapped to the entry ji. So it just switches the rows and columns. Yeah. It has interesting properties. You probably won't see it in first year math. You'll mention it exists, but it has a lot of important applications in something like quantum mechanics, for example. Matrices are very important, and matrices and their complex transposes are, exceptionally important. Yep. Yep. So, yeah. And then I'll also mention, normally, actually, I'll mention that when we get to plotting. Yeah. So there's also operations we can do on these vectors as well. So for example, vectors and matrices. For example, we can do size of B. That gives us the dimensions of B. So the number of rows, the number of columns. Same for the vectors. You can also do something like max of U, and that will give you the largest element in U. Obviously, there's min as well. We can also index vectors. So for example, if I go A11, that's asking me what's the first number in the first row of the first column of A. I run that, it's 1. If I want second row, first column, it goes down to that. So for example, if I put A there again, you can see that second row, first column is 3, and that's what it pulls out there. So you can index matrices like that, and that's something you want to do all the time. You can also do a selection. I can pull out the first row all the way down to the second row. So if, hypothetically, you could have a matrix, a 5 by 5 matrix. You can pull out all 5 rows, but only the first column. But for this example, we can pull out first and second row, first column, and that will give us a vector back, which is just the first 2 rows in the first column. Okay. You can do arbitrary selections. If you have like a 5 by 5 matrix, I could put in some vector here and say, give me the first, the third, and the fifth rows, right? So any vector in there you can use to index. Okay, so that's some real basics on vectors and matrices. Now let's actually use them to do some cool stuff. So one of the very basic things you want to do is plots. All right, that's one of the first things you learn. So what's your favorite equation that you like to plot? Huh? E to the x. Yeah, we can do that. I was going to say y equals x because I'm boring, but let's do e to the x then. So when we want to plot something, we want to basically have an x-axis, right? A vector of x values. We perform some operation on these x values to get a vector of y values. We plot y against x. So let's create a vector x that looks something like this, right? So that's going to create our x-axis. And you can see it worked, woohoo. Because this is going to get messy if I keep creating big vectors, we can actually add a semicolon to the end of the line here, and that will suppress the output. So you can see that I ran it again and it only output up to this bit, and it didn't have output. But you can see it worked because you can go over here and look at x and see that indeed there was a 1 by 21 double. Actually, I might just go over here. Okay, and you can see if I type CLC to clear all the commands, you can see I run this code. You know, if I do clear, it gets rid of all the variables. I run this code, no output, but indeed it's created over there in the workspace. Yeah. Oh, yes, yes, you can add comments as well. %sign, all right? You can do whatever you want like that. I think that this, no, yeah, so I think you can also do Control R, right, to add comments, and is it T? T to get rid of comments, but I always forget that. Okay, so we want to plot e to the x, right? So e to the x in MATLAB, it's not just e to the whatever. It actually has a function exponential. So we can go exp of x, right? And if we run this, you can see it indeed does that. I'm just going to suppress that for now. And to plot, it's really easy. It's just plot xy like that. Okie dokie, I ran that code. And we can see that roughly looks like e to the x. Do we agree? Why is, Zoom, get out of here. Okay. Okay. We can see that roughly looks like e to the x, right? Hopefully we believe me. Yeah. I will just use a simple function just to start with, just to prove a point. That's obviously a linear equation. What if we want to plot x squared? Okay, let's plot x squared. We run this. Uh-oh, there's no graph. We get a big old error. So it says error using the power operator, incorrect dimensions for raising a matrix to a power, blah, blah, blah. So what's happened there? We should be able to plot like x squared, right? Like that seems like a really useful thing to be able to plot. The problem is with the type of multiplication we're doing with the squaring here. So when we write it like this, it's basically saying, let's square our x vector. So it's going to take our x vector and try to multiply it by our x vector. But these are two row vectors. You know we can't multiply them, right? Instead, what we want to actually do is square each of the numbers in our x vector, right? And that's called element-wise squaring because we're squaring the elements. So in MATLAB, whenever we have an operation that acts in a matrix sort of way, we can turn it into an element-wise operation by adding a dot. So you want to do things, you want to do that on things like squaring, so any sort of power, multiplication and division. Obviously, addition doesn't really matter, subtraction doesn't matter, but for those operations, it does matter. And you got to be careful because you won't always get an error. Sometimes you'll have some matrices that actually have the right dimensions to be able to multiply. You'll just get a really unexpected answer. You won't know what's going on. And it's because you missed one little dot on your 600 lines of code. So just be very mindful of including these dots. So now if we have this dot, we can see that we get this function x squared. Okay. Okay, we can pretty this up a little bit. You know, that looked pretty boring. We can actually change like the color of our lines. So for example, if I do something like this, now we get a red line. You can't really see that very well, but I promise you it is red.
Maybe go with something like yellow.
Yeah, let's go yellow. And then we can make it really hard to see. Yeah, you know what's better? Green. Yeah, that's pretty obviously green, okay? You can also change things like the thickness. the markers at each point. I'm not going to go through all those, but you can find the line specifications basically. Okay. There's also a bunch of other types of plotting that is also really useful. So for example, we might want to do a scatter plot. Let's say we don't want to plot like a linear equation, or not a linear equation, but an interpolated equation. Let's say we're just plotting data points. We might want to do a scatter plot. So you can do like scatter xy like this. And now we just get just the points. So that's useful when we have like actual data and we might not know that there's an actual trend. Maybe we want to do like a line of best fit or something like that. So now you can do that. You might also take measurements and want to have error bars. So we can also do an error bar plot. And let's do X, Y. There's a whole bunch of different options, but let's do, I'll just put X as all our errors. So normally you'd put like your, so you know when you have uncertainties, you have like a plus minus a certain amount. So you'd put your X, your minus, your X minus, your X plus. Actually, I think it's Y first, actually. You put your Y minus, your Y plus, so it'd be Y, you know, plus 0.3 minus 0.2, for example. Same with your X and your, so I think it's X minus and X plus. Just for simplicity, I'll put this here and say this is equal to X. Okay. And then we can just write something like this because we don't really want the line if we're doing error bars. We don't want it to interpolate the points for us. We can do line style, none. And hopefully this works for me. Otherwise I'm going to be sad. Uh-oh, Y minus, did I miss one? Okay, Y minus undefined functional variable. That's right. I'll say Y minus equals X, Y plus equals X. Equals X, and that should work for me. Yeah, okay. So now we got some really ugly looking error bars. But you can notice as well though, we plotted these error bars, but we don't have the actual points that we plotted. So this is a pretty useless graph because you know we don't have our actual points. It's just error bars. But we still have the code here for the scatter plot. So the problem is in MATLAB, when you plot something, it gets rid of everything else that you've plotted beforehand. Fortunately, there's a way around this, and we can just tell MATLAB, hey, keep that stuff. And to do that, we can write hold on. So that says whatever is currently the last thing plotted, hold it, keep it there. And then everything else we plot, please keep it, all the way until we see a hold off. And then it's like, okay, this is it. If you want to plot something else after that, you can get rid of whatever. So now if we run this code, you can see that we've got our dots in there as well. And if we really want, we can also plot, we can also move this hold on so that we have our original plot involved. And now we can see that we have our line, our green line, we have our points, and we have our error bars. All right, so that's pretty much everything you'll ever need in like 2D. We can also make a title, right? Whatever you want your title name to be. We can also do X label to label our axes. Y label, same deal. All right, you can see we've got our axes labels and our title. So you can see this is like starting to become a much better sort of diagram, despite the fact I've messed it up, made it ugly. But you can do a whole bunch of other things as well, like put a grid over the background, change the axes ticks, all of that sort of stuff. But I won't go too much in depth with that. I will also talk about how to plot stuff in 3D. So you can plot a surface as well in MATLAB, which is very useful. So to do that, it's a little bit more complicated. But what we do is we use something called a mesh grid. So normally when we plot a line, we start with just a vector, right? Because we only have an x-axis. The problem is when we're plotting a surface in like a 3D space, our domain is like the xy plane, right? We're plotting a surface over like I guess, a rectangular or square or whatever shaped domain. So instead of just having a vector, you sort of need like a vector for each slice of your domain. So if you want a whole bunch of vectors, you basically just want a matrix, right? So you want to create matrices. However, MATLAB will interpret these matrices in a very particular way because they sort of need to be created as like a sort of grid, so the plotter knows how to interpret it. So we have the mesh grid function, which creates the matrices that we need as our domain. So you notice I use this sort of syntax here. So whenever we run a function, it's going to have an output. Sometimes functions will have multiple outputs. So for example, this function spits out an X and a Y matrix. So if I want to save and keep and use those outputs of this function, I have to specify a vector where I want to store each of those output arguments, the two output arguments. So for example, if I want to run this mesh grid command, I can define my X axis. I can define my Y axis. Let's do something like all right. And I will add the semicolon there because this one's going to spit out something gross. Okay, we run that. I might just put it, I'll put it in a separate file just so I don't have to run all the other stuff. Okay, I ran that. We can see we've got big X and big Y over here, 9 by 21 doubles. So it's a 9 by 21 matrix for those. Now, if we want to plot it, well, let's do an equation. What's everyone's favorite 3D surface equation? You can do something cooked if you want. E to the sine X, okay. X of sine X. Do we want to involve Y in some way, maybe?
Yeah.
We could do like times X of sine Y. Are we gonna, is this gonna work?
Ridiculous. We'll see.
Maybe. Uh-oh. What did I do wrong? Yep, I missed the dot. All right. So a sine of a matrix gives me a matrix back where sine acts on every argument of that matrix. Same with the exponential. It exponentiates every element of that. So this whole term is a matrix. This whole term is a matrix. I want to not use matrix multiplication because I'm trying to run a function on the elements. So I want to use a dot there. And you can see if originally I had square matrices, then it wouldn't have given me this issue. It would have just multiplied it, but it would not have given us the thing that we want. So now if we do this, well, we can see it gave us a whole bunch of ugly output. So I'll hide that for now. Now to plot, it's really simple. We do surf of X, Y, Z. And we run that. Oh, we get a cool looking surface. Sick. How easy was that? All right. Cool. Now we can go back to this one. Something I forgot to say is you can add a legend. So blah, blah, blah. I run this code. I get a graph and I get a legend. The green line is this. We can also add arbitrary text to our graph. And I think it goes off the actual points. So we can put some string in there. So I think this will plot text at 1, 1. Yeah. So you can see that it says string down there. And you can add a whole bunch of properties to this text. You can change the font. You can use LaTeX in that as well. So I think if I did something like, I believe it's $. I could do something like this. I hope that works. Maybe it's $2. I don't think it did it? Oh, wait, it did work. Oh, I must have the default interpreter must be set to LaTeX already, so that's fine. Yeah, so you can do stuff like that. So it's got a pi down there. It's really hard to see, but if I zoom in, maybe if it lets me. Oh, well, it's very small, but there is a little pi written there. But you can change the font size and all of that stuff with a whole bunch of extra arguments. Okay. Yeah, so I think that's everything I wanted to say about plotting. That should give you a little bit of an introduction to all that sort of stuff. Again, like you're not going to remember how to do all these line specifications and stuff off the top of your head. So for example, I can make, a dotted line or a dot dash line or something like that. You can just look up on the MATLAB, like, I don't know, it's a wiki documentation, their website. They have like a table. Oh, if you want to do this, then you can do that. When you plot multiple curves, for example, each curve will have a different color by default. So it has like a color scheme. You can change the default color scheme. So instead of using a heat map color where it starts, blue and goes all the way to yellow, goes to red, you can have tropical colors. So it's only greens and blues and yellows and no reds. So there's a whole bunch of different color schemes. Same with the surfaces as well. Like I'm sure as you noticed, the surfaces have particular colors. You can change this as well. I can make this surface just one flat color as well if I want. There's a whole bunch of different properties you can manipulate. Okay. All right, let's look at some control. So in MATLAB's just like any other programming language, you often want to use different methods of flow control in your code. So that means logical statements like for loops, if and else statements, while loops, and there's also switch statements, which we don't really use very often because you can literally do the same things with ifs and else usually. So we won't talk about that. But for example, I'm assuming you guys have all seen if statements before. So if some condition, then some code, and then end is what we always write. So this will be a bit different to like Python, for example. You have to have like a semicolon, a colon here. It'd be different to something like Java where you've got like curly brackets like that, a whole bunch of different things. In MATLAB, you don't have to worry. It's just if some condition and then everything up until our end statement. So what do I mean by some condition? Well, let's say if I have some variable x equals 0. Okay, let's say I have x equals 0. Well, let's say we only want to run this code. Let's say x equals x plus 1. Let's say we only want to run this code. I'll keep that off. If x is equal to 1. So I can do something like this. So this double equals is like a logical evaluation. So instead of a single equals, that's assigning a value. A double equals is a logical check. So this is not a very exciting example because I can run this code. Oh, but it doesn't do anything because, yeah, x is not equal to 1. But if I run it with x equals 1, now we can see that it starts as x equals 1. It runs this code and it gives me x equals 2 on this line 5 here. All right. So there's a whole bunch of different logical statements that we can do. We can also do something like greater than or equal. So now if we run that, you can see that it worked that time. So if x is greater than 1, we can add 1. Yep, it works. You can do same thing with less than. Let's say we want to do multiple conditions. Let's say we want to do x is greater than 1 and x is less than or equal to 10. Okay, that should have run again, I believe. I clear the console. We can see it runs, it works. If we change this code to 9, I'll clear that. We can run it, we see it works. If we clear it again and we run it for 11, oh, didn't run that code. So we can use the AND to have multiple conditions. We can also have an OR, which is a single bar like that. So if either of these conditions hold, we run that. So that bar is just like above the enter key, there's like a straight line above like the backslash or whatever. So shift backslash gives you that straight line, right? People forget about this one. Okay. You can also do not statements. So for example, I could have, we'll run this code if x is greater than 1 or it's not less than 10. Okay, so this not operator. All right, so this not operator, what's a good example? So x is greater than 1, or this is not a good example actually. Let's do x greater than 10. X is not greater than 10. Yeah. So, yeah. So if X is equal to 1, then this statement here will be true and the code will run. If we set X equal to 0, then this is false. That's all right because this is an OR statement. So then it will go and check this one and we'll see, oh, is it true that not X greater than 10? So is X less than 10, strictly less? Yes, it is. So this should run. So we can check that when X is 0. Yep, the code works. All right. So we can also string together a whole bunch of if statements if we want a whole bunch of different conditions. So let's say we want what's a good example? If X is, let's say less than 0, we'll do X equals X plus 1. Let's say we want a different condition if it is positive. We can say else if, I'll make it strictly less than. Yeah. Oh, sorry, not else if. It's else if like this, no space, else if. So if we want a different condition, okay, well, let's say X is greater than 0. Let's do X equals X minus 1, okay? Does that cover all our cases? No, we're still missing a case for 0. Well, we can have something like, okay, well, if X is neither of those, then we can just have an else, some other thing, X equals 100 or something like that. All right, and you can string together as many of these else ifs as you want in between. You don't have to have an else at the end if you've already covered all your cases, but sometimes it's good to have an else in case something goes wrong. But these are the operations, and then it all ends with an end like that. All right. We also have while loops. So while some condition X equals X plus 1. All right. Actually, I'll put this one in a separate. Okay. So for example, we can have while X is less than or equal to less than 5, while X is less than 5, run this code. So we'll see, we run this code. We start off with X equal to 0. It goes into the while loop. X is less than 5. Okay, let's run this. We'll add 1 to X. So we get 1. It goes back to the top of the while loop. Does the condition still hold? Yes, it's still less than 5. It runs over and over and over until eventually it gets to X equals 5. Is 5 less than 5? No. And then it stops. So the last output we get is X equal to 5. What if I have X is greater or equal to 0? Now we've got this thing just adding continuously because there's no termination, right? It's never going to be less than 0 because we started at 0. So what can I do now to stop this? Well, I can hit Control C to terminate the code like that. So sometimes if you don't have an exit, a way of your while loop terminating, then it'll just get stuck like that. And that happens in other bits of code as well. And you wouldn't know, right? If I added a semicolon here and ran this code, you're not getting any output, but when I'm doing stuff, nothing's happening. That's because MATLAB is preoccupied. It's not going to run this code, which is not really code. It's just me spamming, but we give an error. But it's not going to do that because it's still running this, but we don't know that. So if you get stuck like this, it means that something's not right and you need to terminate like that. Okay. Cool. Any questions about that so far? All right, we're going to get to the juicy stuff in a minute. So one last thing, the other method of flow control that we like are for loops. So this is really important because for loops are different in every language, but in MATLAB, basically we go for index equals index vector. So for each number in this vector of indices, run some code, right? So for example, let's say for I in something, well, actually, we shouldn't use I because I is already the complex number, the complex unit. So let's not do that. Let's go k in
Yeah, I'm gonna.
1 to 5, and we'll just say k. And you see if we run this, it outputs each k. All right. And you can put any arbitrary vector in there. All right. So that's most of the basics. Now I'm going to talk about algebra and symbolic expressions, which is some of the really powerful tools that MATLAB can do. So to start with, let's talk about the algebra stuff. The algebra is pretty simple. Often you're going to have to solve equations of the form AX equals B, right? Where A is a matrix, X is a vector, and B is some vector. So they'll give you an A and a B. You want to find X. And you've probably done this in school or something before. You've probably seen Gaussian elimination or something like that, and know that it's a bit of a pain to do by hand. If you want to invert a 4x4 matrix or anything larger than that, it's a pain, right? So fortunately in MATLAB, we don't even need to worry if we want to find X. So for example, let's make A something like 100. What's someone's favorite number? I'm not putting that one. 50. Yep. And let's say our B is 1, 0. That's a boring one. 1, 9. We can do X equals A. Sorry, we can do X equals A, B like this. Notice that this is the different slash to normal division, right? This is specifically matrix backwards division like that, right? The slash goes in the opposite direction. So if we run this, it doesn't like that because what have I done wrong? I want a vector like that, sorry. Yeah, and you can see it inverts the matrix for you using a really efficient algorithm to do that. Another really common problem that you have is finding eigenvalues. So we can do eig of A, and if we run that, that gives us our eigenvalues of A. We can even go further than that. If you recall, every matrix, well, most matrices can actually be diagonalized if they have a full set of eigenvalues using some matrices like this. So this is probably don't know this unless you've done some algebra, but basically any matrix you can, well, not any matrix, but a good set of matrices you can diagonalize, put their eigenvalues on the diagonal with some other matrices that you can use to sort of rotate into a different basis. So we can actually find these as well using the same sort of function. So if we do V D like this equals eig of A, now we get these V. So these are the eigenvectors as well as these matrices that transform, and also the eigenvalues here. So this is really useful because if you have a really big matrix, you don't want to do this by hand, all right? Or even a matrix with complicated expressions or algebraic expressions. You don't want to do it by hand. Okay, all right. So let's look at symbolic expressions. So this is probably the last thing we're going to look at today, but I think this is a really, really important tool, especially, well, you'll see if you want to do any sort of, well, not linear algebra, but just algebra in general. So symbolic expressions, what does that mean? So at the moment, everything we've been dealing with in MATLAB has just been raw sort of numbers, right? You know, I assign a value to X, I do Y equals X plus 1. MATLAB doesn't make a distinction, you know, what these variables are. It just sees the raw numbers, right? So, you know, if I have Y, I can't go back and go, oh, how did I get Y? Oh, it was X plus 1, you know. When I run this code, the only thing that's stored is Y equals 2. I can't see what expression I used to get Y. I can't do any manipulations. You know, I can't take a derivative. So for example, if I had Y equals 3x squared, all I get is the number 4. It's like, well, how did I actually get that Y value? Hello. And if I want to do some expression, some manipulations, I'll be doing a MATLAB talk. You know, what if I want to take the derivative, for example? You can't do that, right? MATLAB just sees numbers. Fortunately, we have something called the Symbolic Toolbox, which is really powerful. So I'm going to give you, well, let's give you a quick example. Now, if I do like sims and I create a symbol x, I can do y equals x squared or something like that. And if I run this code, we can see that instead of, so before when we had x equals 1, y equals 4, now we have y equals x squared, right? It actually recognized that it's a symbolic expression, a y as a function of x. So that means we can actually do like interesting stuff, right? We can manipulate these equations. We can take derivatives. We can solve equations, like factorize polynomials and stuff like that and find their roots if we write them as symbolic expressions like that. So for example, just a really simple example, I can differentiate y with respect to x, and we get the answer is 2x. So I'm sure you can see how powerful this is, right? So I'm going to give you a bit of an example that's useful, particularly for labs in physics. And you'll probably wish that you were doing this for ages. So in physics, often you have to do uncertainty calculations, and the uncertainty expressions get pretty cooked.
Wait, you do that with MATLAB?
Oh, yeah. Yeah, I'm going to break your heart by showing you how easy it is in MATLAB. Oh, yes, a recording will be made available of this after. Yes, we're recording it. Yes, so let's say I have some function f. That can be anything, right? You might have a regression that's like r times d times t over x plus y, or some cooked expression with your physical constants and stuff like that, and all your measurements have different uncertainties. What we can do is create some function f, right? And we can create a vector of symbolic variables. So we can go sim of x1. We can go sim, I think these want to be these, sim of x2, for example. I'll just do just 2 of them. All right, I can run this code. What have I done wrong? Sim, equals. Okay, now I have a vector x with 2 symbolic variables, right? So these could be my variables that I measure in the lab, right? So it could be voltage and current or something if we're measuring, I don't know, maybe f is a function for intensity and we measured the voltage and the current. We can have those as voltage and current. We also have our uncertainties. So I'm just going to call that, let's call it x1u and x2u, u for uncertainty. All right. So let's say, so let's say, now let's actually define our function f. So let's say our function f was written as something like, let's say x1 plus x2 all over x1 minus x2. That might be useful if you're doing something, something like a reduced mass. Yeah, I don't know, something like that, right? So we can run this. What did I do wrong? Oh, sorry. You want to do x of 1 and reference the x vector because these are just the names. X of 2, x of 1, x of 2, right? And now you can see we've got some symbolic expression like that. So now you can sort of see, so if you remember with uncertainties, there's a formula for calculating uncertainty of arbitrary functions, of arbitrary variables. So they give you a bunch in like your first year lab saying, oh, when we add variables together, if we add variables together, their uncertainties add in quadrature or something like that, or maybe multiplication. Doesn't matter, you won't need to remember it because you can do it much simpler, right? So let's call this expression, and we can say, let's differentiate f with respect to x of 1. Well, let's do something a bit more than this. So when we actually want to compute our uncertainties, remember we take the derivative and I believe we multiply it by our uncertainty, right? So let's do xu1 and we square it. Does that sound familiar? And we do the same thing for our other variables. So we differentiate our functions, we multiply it by the uncertainties, and then we square it. All right. Let's see if there's any typos. You get some big ugly expression like this, but that's your uncertainty expression, right? Which would have sucked to do by hand with all these different derivatives. All right, so now we have this expression for the uncertainty. All good. Well, this is literally just your expression for your uncertainty, right? This is what you would have to compute by hand normally and take tons and tons of partial derivatives and multiply things and square things and take square roots and stuff like that. Still looks pretty ugly though. Well, we can actually do some stuff with this, right? In fact, you can literally turn this expression straight into LaTeX, straight into code that you can copy and paste into a report or into, Word or anything like that. So we can just LaTeX it. I'm going to write combine. I think that just simplifies the expression a little bit. And let's do expression like this. Now if we run this code, we get some LaTeX like this. So now you can literally, that's ready to go straight in a report. So instead of by hand doing 100 bloody partial derivatives, because sometimes it won't just be 2 variables, right? It'll be like 6 variables. And then you've got to take 6 lots of partial derivatives of some function with square roots and powers and logs. And it's like, no, you could spend an hour doing that, or you can do it in a couple lines in MATLAB. So I would definitely recommend writing yourself a generic script like this. It'll save you a lot of time because you can just change these variables to whatever names you want. You just change this expression and then it's all done. I think for my version, I wrote like a for loop that goes over the actual size of these expressions. But yeah, so then you can do all that computation, get a nice looking equation. You don't even have to worry. You can also actually evaluate these functions now with numbers. So at the moment, f is just some expression. If I actually want some actual values or some uncertainties in f, what I can do is actually use the subs function. So I can do f equals subs. So what do we want to do? We want to substitute some values in f. So the first argument is f. We want to replace x1, for example, and we want to replace it with a number 2. And if we run that, now we get the same thing with 2. And we can run it again. And we can change that to a 2 and make it like a 3. And now it computes it like that. Simple. We can do the same things for our uncertainties in this expression here. Finally, what you probably want to do is just write f equals double of f, because sometimes you might have like a pi left in there or something that, depending on your formatting, it'll keep it in there as exact values, depending. But then that should do that. All right. So that's a really powerful tool. You can do any sort of derivatives and stuff like that, a whole bunch of other functions. The last thing I want to mention about symbolic stuff is solving. So you can actually solve an equation. So for example, I believe the syntax is, let's say 2 equals x1 plus 1. We can put in some parameters to specify that it's real numbers only. And I think there's a true that goes in here, which just tells us to, what was it? True or true? True? True, lowercase true, yeah. Changes in every language. Okay, and I think, I made the same mistake as before. This has got to have brackets. Okay, and we see it solved that equation, right? That was obviously a really simple one, but if you have like some long gross polynomial or some polynomial that's to like a really high order, you don't know how to solve polynomials that are like x to the 5 minus, x to the 3. So something like x to the 5 minus x to the 3. And I will take away this real parameter because it might be complex. Oh, whoops, sorry, I put the 3 in the wrong spot. X to the 3. And I get rid of this. All right, and now it's giving me all the different roots. Okay. Cool. Or did it? No, hang on. Let's keep. I think the true was important. Yeah, I think the 5. I think it's fine actually. I think I think the 5 is the actual value of the root, right? So I think it rearranges this to say this is equal to 0. Yeah. But yeah, I'm sure you can see how powerful that is. If you have some cooked expression that you can't be bothered rearranging, you just whack it in MATLAB as symbols, does it all for you. And these symbols also work with matrices. So if you want to find eigenvalues of a matrix, so for example, if you're doing a quantum mechanics problem and you have a splitting between two of your energy levels of a splitting of like delta, you can put delta in as one of your symbolic variables, solve the eigenvalues of a 4x4 matrix in terms of delta. And then you go, yeah, I wrote that. I did that by hand. But no, it's all done in MATLAB symbolically, which you're allowed to do in your assignments. Hint, hint for your quantum assignment. Not this one, but probably the next one. Yeah. Yeah. Okay, I think that was pretty much everything I wanted to cover. I know we started like really basic and then got a bit cooked pretty quickly. But those are just some basic functionalities. Some of this stuff won't be useful to you guys just yet, but it's something to be aware of that you can do because it'll be very powerful when you come into some problem that's difficult to solve. But I think we're going to finish up here. So if anyone has any questions, I'm more than happy to answer them.